Hello, Dan here from howtomechatronics.com. In this video, we will learn about electric field, the properties of electric field lines, and the superposition principle. Two electrically charged objects exert a force on each other. They also exert a force on each other even when they are not in contact. This force is called an action at a distance force. If we have a charged object, we can actually predict what will happen to the other electric charges when they are brought close to the other object. A charged object modifies the space around it, forming an electric field. The electric field has an ability to act with a force on another electric charge placed at any point of the field. When we talked about Coulomb's law, we observed the force between two charges as an action between two objects. And now we will observe the force as an action that the electric field exerts on the charge that enters that field. So what is an electric field? Michael Faraday was a British scientist and was the first person to introduce the concept of electric field. A field can be any quantity that can be given a value at all points in the space around the source of the field, or a region of influence. But how electric fields work? First of all, the strength of the electric field is a vector quantity, having a magnitude and direction. The direction of the electric field at a point is actually the same direction as the force acting on a positive charge placed at that point. Let's say there is a positive point charge, denoted by capital Q. In order to see the effect this charge has on other charges, we will bring in its sphere of influence a small positive charge, denoted by lowercase q. The reason we bring a small test charge is because we want a value that is independent of the size of the test charge and depends only on the field source and the distance from the source. A test charge is always positive by definition. Both charges create electric field, but big Q has much larger magnitude than small q. The point charge Q modifies the space around it and sets up the electric field. Now we can measure the electric field. The electric field generated by a charged object is in fact the electric force between the object and the test charge divided by the magnitude of the test charge. Coulomb's law will help us find the force. In place of capital F, we will use the Coulomb's law equation. Here we can notice that the small q appears twice in the equation. So it cancels out and we are left with an equation that includes only the point charge. Finally, the strength of the electric field created by a point charge is equal to the Coulomb's constant multiplied by the charge of the object generating the field and divided by the distance between this object and the test charge squared. Here we have positive point charge and positive test charge, and the result has a positive sign, meaning that the positive test charge would be repelled by the positively charged object. That's why the electric field diagram has arrows pointing outwards. For negative point charge and positive test charge, we have an attractive force which is shown by the negative sign in the equation. The electric field line diagram for negatively charged object would look like that one of the positively charged object, but with the arrows pointing inwards, which means that the positive test charges would be attracted to the negatively charged object Q. The unit of measurement for electric field is newtons per coulomb, or volts per meter. Electric field exists even if there is no test charge nearby to measure it. Similarly, a gravitational field surrounds the Earth even if there is no test mass nearby to measure it. If we know the value of the test charge and the value of the strength of the electric field, we can easily calculate the force by simply multiplying those values. For example, we have a point charge equal to 1 times 10 to the minus 8 coulombs. Also, we have a test charge of 1 coulomb at a distance of 50 centimeters. So, what is the electric field 50 centimeters away from the point charge? The electric field at that point is going to be Coulomb's constant multiplied by the charge generating the field and divided by the distance between the point charge and the test charge squared. Let's put the numbers here. This is equal to 9 times 10 to the 9th Newton meter squared per coulomb squared times 1 times 10 to the minus 8 coulomb divided by 0.5 meters squared. Here we can cancel out meters and coulombs, so we are left with newtons per coulomb. This is equal to 90 divided by 0.25 newtons per coulomb. Finally, the magnitude of the electric field that the point charge generates at 50 centimeters distance is 360 newtons per coulomb. The force exerted on the test charge is going to be equal to the test charge multiplied by the magnitude of the electric field, which is 1 coulomb multiplied by 360 newtons per coulomb. Here the coulombs cancel out, and the force exerted on that 1 coulomb of charge is going to be 360 newtons. Here we can notice that both the point charge and the test charge are positive, so the force will be repulsive, meaning that the direction of the force will be outwards. Superposition principle applies to electric fields as well. Let's say we have 2 point charges, Q1 and Q2, and we bring a positive test charge Q nearby. Q1 is positive and Q2 is negative charge. The force that Q1 applies on Q is repulsive, and the force that Q2 applies on Q is attractive. The superposition principle can help us calculate the total electric field created by the multiple point charges, which is simply a sum of all individual fields. In other words, the total electric field from a system of charges acting on a test charge is equal to the vector sum of the electric fields at that point from each of the individual charges. Using the equation for electric field, we can calculate the total electric field E, which is equal to E1 plus E2. The total electric field is represented with the vector E1 plus E2. A small positive test charge Q placed at the various points near Q would be repelled or attracted by Q and would move along the lines. These vectors are called lines of force or electric field lines, a concept first introduced by Michael Faraday. They show the direction and the magnitude of the force applied on any nearby positive test charge. It is actually the direction that a mobile positive charge would move if placed in the field. Let's take a look at the field between two charges of similar magnitude but opposite sign. They form an electric dipole. Now, let's connect their electric fields and create a total electric field. If we pay attention to this total electric field, it will reveal 4 important properties of electric field lines. The lines always begin on positive charges and end on negative charges. In our example, the lines start at the positively charged object and move toward the negatively charged one. We can notice that the same number of lines come out of each particle because the magnitude of their charges is equal and opposite. The field lines must be tangent to the direction of the field at any point. The closeness of the lines indicates the strength of the field. The greater the line density, the greater the magnitude of the field, and opposite. The lines never cross. A charge cannot go in 2 directions at the same time. Okay, so that would be all for this video. In the next basic electronics video, we will talk about work and potential. Thanks for watching. I hope you enjoyed this video and learned something new. Don't forget to subscribe, and for more tutorials visit my website howtomechatronics.com.